Alright, well, welcome back. We're doing section 3.3 now, Isomorphisms and Homomorphisms. So here's the idea in terms of this. When you look at the idea of a mapping, we're going from Z5 to a set that we created, 0, 2, 4, 6, and 8. And this set is actually a subset of like Z10. So we're looking at this by, we're going to create a mapping. And this mapping here, 0 element of Z5, Z5 is 0, 1, 2, 3, 4. We're going to all the way to, we're going to map these guys over to this new set, 0, 2, 4, 6, and 8. And I have 0 equivalence class mapped to 0, 1 equivalence class is going to map to 6, 2 equivalence class is going to map to 2, 3 equivalence class is going to map to 8, and the 4 equivalence class is going to map to 4. Now, in our textbook on page 71, they created a chart, and we're going to be talking about S is going to have the same structure under multiplication and addition as the Z5 set. So we created this mapping over, and we took the addition table and the multiplication table, and we just basically substituted. So here's our textbook right here, and this is what we're referring to here. So we're creating this addition table in S and a multiplication table in S, but where it was really come from is, and Dr. Hungerford put the little bar notation over the little pointing brackets that it usually does just for ease of typing it in, I think. So all he did was take the multiplication table and the addition table and multiplication table for Z5 and just replace the elements within the set to create these new sets up here. So this idea of literal substitution is the idea of what we're referring to in this chapter as isomorphic. These two sets are actually isomorphic to one another. So, isomorphic rings are rings that have the same structure in the sense of multiplication and addition. You get that one-to-one mapping for each one of those elements, and so, but also this idea of the addition and multiplication hold over. Now, why is this isomorphic ring important, this idea of isomorphic rings? What can you do with this modern algebra stuff that we're teaching you guys? Well, one of the big deals about modern algebra, and it is very, very important in this day and age, is that idea of code theory. Now, the military's been using this for years, but because of credit cards and the like, the idea of being able to disguise information and code it while it's out there on the net or whatever the case may be, like when you go to eBay and you use your credit card to buy something or other, you type in your credit card number. How does somebody not get your credit card number? Well, if someone breaks the system, hacks into it, they can, but the whole idea is your credit card numbers are actually coded. Again, we've been doing this for years, ever since the military, and hiding our secrets and our communiques and things like that. But in modern days, because of the age of computer, the idea of security systems is very, very important. And what this is doing is you've got two rings up here. You've got two rings. You've got a Z5 ring, and we've got this made-up ring S. But if you just looked at S, it may be more difficult to follow. Granted, this one only has 5 terms, but imagine it having a lot more terms. And it would be much more difficult to figure out the pattern. But if you knew it was the Z5 pattern, well, then you already know that kind of math. You had a test on that not too long ago. So this idea of code theory is where this stuff is going to be at. So when you have two rings that are isomorphic, not only do the elements map over, but their operations, the addition and the multiplication, also match over. That's called an isomorphism. They're basically the same thing, but one ring has got the code for the other ring. And so the mapping itself actually becomes the code of how you convert, and if you can go one way, you can also decode and come back the other way. So, definition. A ring R is isomorphic to a ring S, and this is the notation, R with an equal to with a squiggle on top of it, tilde S. That's the notation for R is isomorphic to S. If there is a function f that maps R to S such that f is injective, that means 1 to 1. F is surjective, that means on to. And number 3, f of a plus b is equal to f of a plus f of b, and f of a times b is equal to f of a times f of b for all a and b and r. In this case, the function f is called an isomorphism. So the function itself is isomorphism. The two rings, as comparison to each other, are isomorphic. So you've got to have basically 3 things going on here. You've got to have the injective, surjective, that one-to-one onto idea, and this definition right here. This is not only mapping the elements in R, it's actually mapping the operation. So f of a plus b is equal to f of a plus f of b, and f of a times b is equal to f of a times f of b. And just to remind you, inside the parentheses, this is kind of like f going from R to S. R is the domain, S is the range in high school terms here. This addition inside the parentheses is coming from R. This addition outside the parentheses is coming from S. This multiplication a times b is coming from R, but when you map it over, that'll be f of a, which is an S, times f of b, which is S. So this multiplication is an S. So this is the idea of isomorphism. But you may have forgotten your old one-to-one onto concepts when we're using the big words for this one now. You're in junior level math classes now. Injective, which means one-to-one, and surjective, which means onto. So remind ourselves of some definitions here. Recall that the function is injective, or one-to-one, if f maps R to S and for each element S, X in R, there exists only one element Y in S, such that f of X is equal to Y. And to prove that a function is injective, one-to-one, what you do is if you have f of R1 is equal to f of R2, then you need to show me that R1 is equal to R2. So you give yourself 2 elements. F of R1 is equal to f of R2, and you manipulate the function, and if you end up showing me R1 equals R2, then the function is injective. A function is surjective, or onto, if you got this mapping, f going from R to S, and for each Y in S, there exists an element S, X in R, such that Y is equal to f of X. Now, let's talk about these two guys together. First off, we'll focus on the surjective. Surjective means onto. R is the domain, S is the range in layman terms here. So you've got this S over here. What it means to be onto, that means everybody in S, every element in ring S is going to be mapped to. So you can pick any Y in S, and there will exist an X over here in the R world, the domain, such that that Y is equal to f of X. There may be more than one X that maps to Y, that's okay, but there's going to be only one X. I mean, there's going to be a Y. You're going to guarantee there's going to exist an X that maps to it. Now, the other one is injective, one-to-one. Now, you got one element to one element. One element R will absolutely map to one element in X. You don't have multiple elements in R mapping to S. You could have that. That would be a function. That's fine. But a one-to-one function has one element in the domain mapping to one element in the range. So in high school, injective, which we didn't call it that, we called it one-to-one, was shown or proven by what we call the horizontal line test. Now remember, the vertical line test goes up and down. So the vertical line test shows you have a function. A horizontal line test, running from left to right, when you have a horizontal line and it intersects your graph, you look at the graph, and if a horizontal line intersects the graph at more than one spot, it's not one-to-one. It's not injective. If a horizontal line only intersects the graph at one spot, then we call that injective. So this was that horizontal line test. But the problem with that definition from high school is you were required to graph the function. Well, we're playing around with the rings, and there will be no graphing of this particular material. We got mappings is what's going on. Your next definition, and this is the important one, we define the idea of an isomorphism, but you need more information on that, and the more information on that is something called a homomorphism. So let R and S be rings with A and B be elements of R. Also let and I'm going to start using Greek letters at you guys, so get used to this. Phi of R going to S, phi maps R to S, be a mapping from ring R to ring S such that f of A plus B is equal to f of A plus f of B, and f of A times B is equal to f of A times f of B. Just that third part of that isomorphism. Then the phi of going from R to S is called a homomorphism, and R is homomorphic to S. This mapping is a homomorphism. Now, a couple of things I want to point out in terms of this definition that I'm really going after here. You know, I put a little subscript R into this guy. So I want you to understand, A and B come from ring R. And I put a little R inside, underneath that little plus to let you know what kind of adding we're doing. So f of A plus B inside of R will be equal to f of A plus f of B. But this addition is inside the ring S. So once you map the guys over, so before you map them, you're adding an R. After you map them, you're adding an S. But this is going to be equal. Same idea here. This is the multiplication R. So this will be f of A times B, and the A times B is inside R because A and B came from R. But that will be equal to f of A, which is an S, times NS, f of B in this S. So what's going on here is not just the elements are mapping over, but the operation is mapping over. That's a homomorphism. And that's very important. And it's more than just a regular function that you studied in junior high school and high school. These guys are real special here. So I put F here, but they're actually, instead of calling them F, which is the way the textbook does it, these guys are real special. They're not your standard functions. So what's the Greek letter of F is phi. So we're talking about phi of A plus B is equal to phi of A plus phi of B. And phi of A times B is equal to phi of A times phi of B. And again, this is a classic notation to emphasize that we'll put a Greek letter on this guy. Not always. Dr. Hungerford's big into, as I copied the definition down, using regular letters. But these are more important than the old f of x equals 2x plus 5 or whatever the case may be. Those guys are typically, those are just functions. Those are not homomorphisms. So we're going to emphasize homomorphism. So I'll throw some Greek letters at you for these mappings, but don't be concerned. Alpha, beta, gamma, delta, phi type things here. So there we go. And so again, to make sure I emphasize this, note that phi is a very special function, such that it not only maps R to S, but it preserves the maps of addition of plus and ring R and times under ring R to plus under ring S and times under ring S. So it preserves not only the elements mapping over, but it preserves the operation. Addition plus in ring R is going to map to plus under ring S, and times in ring R maps to time in ring S. So we call these homomorphisms, or what we call property preserving mappings. They preserve the properties, and that's a very important thing to have, and that's what you want to have if you're creating code theory. So can I give you guidelines of where this stuff is actually used in your future and things like that, especially for your computer science majors and stuff. This is very cyber security type concepts and stuff that we're doing here. So homomorphisms are property preserving in terms of going from one ring to the other ring. So let's talk about an example here, just to kind of give you a feel for this. All right, so this is an example. Let K be the famous 2x2 matrices, but we're going to be doing something special with these 2x2 matrices of the form A, B, negative BA. So we're really only using two entries, A, B, but then on the second row, it's going to be negative BA, where A and B are real numbers. So I'm trying to give you kind of a concrete looking function here. So your entries in your matrices are coming from the real numbers. All right, but it's a special matrix, A, B, negative BA. And we're going to let C be the famous set of complex numbers. You remember complex numbers. A plus BI, where A and B are real numbers, and I is equal to the square root of negative 1, the famous imaginary numbers. So imagine if you could take the square root of negative 1 and you come up with this complex number, A plus BI. A is called the real part, B is called the imaginary part of your complex number. Now we're going to create this mapping. We'll call him F. Okay. So F takes K into the complex numbers such that, and here comes the mapping, got to define these mappings here. F of K, which is a special matrix, A, B, negative B, A, that's going to be equal to A plus BI. Now the question is, of course, is this function, is F, an isomorphism? So, is this thing going to be an isomorphism? So we're going to end up proving it. Yes, it is. The answer is going to be yes, but the only way you can tell that is you actually have to go through the definition. So here we go. If you remember your definition of an isomorphism, you're going to have to prove three things to me. So I kind of set up my papers accordingly here, but here they are. You got to prove it's going to be injective, 1-to-1. You got to prove it's surjective, which is onto, and then the other thing you're going to have to do is prove it's a homomorphism. We've got to show that f of a plus b equals f of a plus f of b, and we've got to show f of a times b is equal to f of a times f of b. So it's kind of a big to-do to be able to prove an isomorphism. So let's go through this. All right, to show injective, 1-to-1, you got to give yourself two elements in your domain. So I'm going to set myself up here. I'm going to let a, b, negative b, a, and I give myself another matrix, c, d, negative d, c, be elements of K, where, of course, a, b, c, and d come from the real numbers. Okay. Now, to show, so I've given myself a couple elements in that set K. There's 2x2 matrices, and to show that it's injective, I'm going to do this. Let f of this matrix a, b, negative b, a equal to f of the matrix c, d, negative d, c. Okay. Okay. Now, then, this implies what? If I map f of a, b, negative b, a according to my f map, that's equal to a plus bi. And that's going to be equal to, if I map f of c, d, negative d, c according to how we define f to map, that would be c plus di. So that is by substitution. I replace f of a, b, negative ba with a plus bi. I replace f of c, d, negative dc with c plus di. Now let's talk about what happens when two complex numbers are actually equal to each other. This gives us, well, to be two complex numbers are equal to each other, that means that the real part, the a, has to be equal to c, the real part. Real part on the left has to equal to real part on the right, and the complex part, which is the imaginary part, the bi, that means that the b has to be equal to d. And so with a equals c and b equal d, then this a, b, negative b, a matrix would have to be equal to c, d, negative d, c. So I started out with f of a, b, negative b, a matrix equals f of c, d, negative d, c matrix, and then I end up showing you that the matrix a, b, negative b, a equals negative c, d, negative d, c. So f of R1 equals f of R2 implies R1 equals R2, and that means therefore f is injective. This is how you prove something is 1-to-1 when you can't do the horizontal line test. You actually have to assume f of R1 is equal to f of R2, and then manipulate your function to show that R1 has to be equal to R2. That makes it injective. So there's injective out of the way. Now I want to show surjective. Now, surjective is actually a wee bit on the easier side, that is, and it is this. So surjective, remember, f is mapping basically from K into the complex numbers. So with surjective, and I'll remind you, surjective is the same thing as the old word onto from high school there. You've got to pick an arbitrary element over here in the complex world. So we're going to pick yourself a guy. C plus DI be a complex number, where obviously C and D are real numbers. Okay, so there's my complex number, C plus DI. Okay. Then, who has to map to them? Then has f of C, D, negative DC, according to the way we define how to map this guy, that's equal to C plus DI, and as this matrix C, D, negative DC is an element of K, where C and D are real numbers. Thus, F is surjective. All right, I know you're looking at this going, wait, that's too easy. Yeah, exactly. Surjective is actually quite easy. All you got to do is pick an arbitrary element over here in the range, the complex numbers in this case, and you just got to figure out who must have mapped to them. And you make sure who the guy that maps to them came from that set K. And so surjective is pretty straightforward, but it's the idea that this C plus DI complex number is very ambiguous. It's just an arbitrary complex number here. And so any element in the complex number is going to be mapped to. That means it's surjective. So it's a very straightforward kind of concept when it comes to surjective. Now the big one obviously shows up when it comes to the third case. And the third case is the homomorphism. Okay? So, to show the homomorphism, what we're going to do here is this. All right? Remember, we're going to give ourselves a couple of elements. So, once again, let the matrix A, B, negative BA, and the matrix C, D, negative DC be elements of K, where A, B, C, and D are real numbers. Now, homomorphism is the idea of the mapping. Remember from our definition, f of A plus B has got to be equal to f of A plus f of B, and then I got to show f of A times B is equal to f of A times f of B. So that's exactly what we're going to do with these elements. So, what is f of matrix A, B, negative B, A plus C, D, negative DC? Well, according to my matrix addition here, that's the same thing as f of the matrix. When you add matrices, you add their components. A plus C, B plus D, negative B minus D, and A plus C. And according to F mapping a element in K, this would end up being A plus C plus B plus D times I. Now we're going to compare this. Now, what would f of the matrix A, B, negative BA plus f of the matrix C, D, negative DC be equal to? Well, this would be by substitution here. Well, first off, f of A, B, negative BA, that's how we defined how the f was, that would be the complex number A plus BI, plus, how would you map f of C, D, negative DC? That maps into the complex numbers as C plus DI. And how do you add complex numbers? You add their real parts and you add their imaginary parts. So this will be A plus C plus B plus D, denoted with an I. and they're equal to each other. Therefore, f of AB negative BA plus CD negative DC is equal to f of AB negative BA plus f of CD negative DC. And I've got the first part of my homomorphism taken care of. F of two elements being added will be equal to f of the first guy plus f of the second guy. So that's kind of like your part one of homomorphism. And then the part two of homomorphism, we got to work on the multiplication stuff. Okay? So here we go. On the multiplication, we continue on. What would f of the matrix AB negative BA multiplied times CD negative DC? Who's that guy going to be equal to? And I'm going to put my little dotted line here. So now we're focusing on the multiplication. So I'm going to slide this up so you guys can see this. So first thing you want to do is you want to multiply your matrices. So how do you multiply matrices? Row by columns, of course. So it'll be first row, first column here. A times C and minus B times D. That'll be the first element. First row, second column, A times D plus B times C. First row, second column. Second row, first column will be minus BC minus AD. And then second row, second column would be minus BD plus AC. Remember, all A, B, C, and D are all real numbers here. So you notice that you're going to get a matrix of the same format. The main diagonals are equal to each other just because it's AC minus BD. That's the same thing as minus BD plus AC. And the off diagonals are the same thing except opposite. AD plus BC. This is minus BC minus AD. They're the same thing. We'll factor out the negative. So there we go. And now I'm going to map it. And when I map this over, this will give me AC minus BD, that's the real part, plus the complex part of AD plus BC. You need to note it with an I, the complex part. Now, compare that to f of AB negative BA times f of CD negative DC. Now go ahead and individually map the elements over by substituting. So f of AB negative BA is actually A plus BI. Then you're going to multiply that times f of CD minus DC would be C plus DI. Now we're in the complex world. So in the complex world, when you're multiplying, you're going to literally FOIL it out, first, outer, inner, last, distribute if you like. So here we go. We end up getting A times C plus A times DI plus B times CI plus BD. I times I is I squared. And remember, I squared by definition is equal to -1 in the world of complex numbers. So this ends up giving you AC plus ADI plus BCI. And then with I squared being -1, that becomes minus BD. I'm going to put together my real parts. So this ends up being AC minus BD. And I'm going to put together my complex parts plus parentheses, factoring out the I, AD plus BC times I. And notice you get the same thing. Therefore, f of AB negative BA times CD negative DC is equal to f of AB negative BA times f of CD negative DC. And hence we have f is a homomorphism. And 3 dot means therefore, in terms of my example, therefore, f going from k to the complex numbers is an isomorphism. What does that actually mean? That means that even though, go back all the way over here, even though we have 2 different functions here, okay? This guy right here. We got complex numbers, which are the 2 by 2 matrices here, in the form of A, B, negative BA. And we got the complex numbers of the form A plus BI. This is matrix multiplication. This is complex number multiplication. These are completely 2 different kinds of numbering systems out there. 2 completely different kinds of rings. But the reality is they may look different, but when you create an isomorphism, they're the same thing. They may be disguised, but they are the exact same thing. So, which means in terms of ring theory, remember I always ask you the question, how many rings are actually out there? And the answer is there's an infinite number of them. But you got to be careful, because if you can create an isomorphism from one ring to another ring, they may look different, but in essence they're the exact same ring. So this kind of cuts into the actual number of rings that are out there, because a lot of rings will be isomorph. They may look different, but they're actually the same ring. You just redisguised how you're going to multiply and how you're going to add from one set to the other. But once you get that isomorphism, you can declare them to be isomorphic. The 2 rings are isomorphic, which means they may look different, but they're the same thing. But if you're looking at it from a code theory perspective, that's exactly what you want. You want an isomorphism where you've got, something that's disguised, that's hard to follow, but you actually know what the world you want to play in is, and actually know how to manipulate in that world. There's your data actually in real time stuff that you actually can read off. But if I want to code it, you don't want to make sure that no one else can read it except for the people that you want to read it. So you want this isomorphism because it's basically the same thing, but you got to have the function is the code. All right. But as I mentioned to you guys before, functions, most functions, are not homomorphisms. Homomorphisms are real special. That's why I give them that kind of designated Greek letter mapping instead of just F and G. And Dr. Hungerford in our book likes the F and G's and H's and stuff like that. So he makes them look just like old functions from high school and stuff, but they're much, much more than that. That's so most higher level math classes, especially in the commuted ring theory, modern algebra world and stuff like that, typically give mappings a special designation with like a Greek letter or something like that to let you know they're more than just functions. See, most functions are not homomorphisms. For example, I just picked one. F of x equals 2x plus 1. Well, let's just check the homomorphism definition here. So let's check what is f of 3 plus 4 and compare it to f of 3 plus f of 4. Well, f of 3 plus 4, same thing as f of 7. F of 7 would be 2 times 7 plus 1, which is 15. F of 3 plus f of 4, well, f of 3 would be 2 times 3 plus 1, which is 7. And f of 4 would be 2 times 4 plus 1, which is 9. And 7 plus 9 is 16. And since 15 doesn't equal 16, they're not equal to each other. Therefore, this guy is not a homomorphism. Most functions are not going to be homomorphisms. These homomorphisms are much more elaborate with the idea of you map the elements, but you also have to map the addition and the multiplication. So you have a big theorem here, and that is Theorem 3.10. When it comes to these mappings, you're going to have some very special properties. So, And again, there's a couple of things I want to define for you as I talk about Theorem 3.10. So here's my wording. Let F, I'm copying this out of Dr. Hungerford's book, otherwise I would have used phi or something or other. Let F go from ring R to ring S be ring homomorphism. So this is going to be my new fancy word right here. Just to remember, mathematicians are inherently lazy. We're always looking for shortcut ways of writing stuff out. When you call a function a ring homomorphism, that tells you like three things. One, F is a homomorphism. It also tells you that R and S are actual rings. So when I say F goes from R to S be a ring homomorphism, that just screams volumes, and all I have to write down was two words. So F is a homomorphism, R and S are rings. But then here comes your properties. Under homomorphisms, zeros map to zeros. F of 0R is equal to 0 and S. Remember, R and S are rings. The zero element in R is called 0R. The zero element in S is called 0S. So F of 0R is equal to 0S. 1. Number 2, the additive inverses map to each other. So F of negative A will be the same thing as equal to negative F of A for any A inside of ring R. So you pick an element in your, quote, domain here, A, and you go F of negative A, that's equal to negative F of A. So you can pull the negative out of a homomorphism. And because of that, you get for free, property number 3, you're going from that negative element to the concept of subtraction. So here's F of A minus B is equal to F of A minus F of B for all A, B, and R. This is from property 3.10. From the definition of homomorphism, we know that F of A plus B is equal to F of A plus F of B, but from Theorem 3.10, then you can put the negative in there, or the subtraction. F of A minus B is equal to F of A minus F of B. That will work with all homomorphisms. Continuing on, if R is a ring with identity, okay, so we're talking about our domain guy over here, the ring R. If ring R is a ring with identity, and F is a surjective, that means it's on to map, then I got a couple more properties for you under homomorphisms, and that's that multiplicative identity. F of 1 and R has to be equal to 1 and S. S will also have to be a ring with identity. Even though R is a ring with identity, if you give me a surjective map, automatically that 1 is going to have to map to a 1 over there in the S world. So S will have to be a ring with identity. The additive identity and the multiplicative identity have to map to each other under homomorphisms. F of 0R equals 0S. Now, not all rings have an identity, but if it does, F of 1 in R will be equal to 1 in S. And number 5, whenever U, element of R, is a unit in R, then F of U is going to be a unit in S. Remember what unit means. Unit means it has a multiplicative inverse. So only do the additive inverses map, the multiplicative inverses map. So whenever U is a unit in R, then F of U is going to be a unit in S, such that F of the U inverse is equal to F of U inverse. So this is the multiplicative inverse of U. That will map to the multiplicative inverse of F of U. That's what we're saying here. Okay? So under Theorem 3.10, we have a lot of properties to disseminate here. Standard 3 properties: F of 0R equals 0S, F of negative A equals negative F of A, and F of A minus B equals F of A minus F of B, all under homomorphisms. And if I happen to have R as a ring with identity and F is a surjective map, it has to be on to, so everybody over there in S world gets mapped to, then F of 1 in R equals 1 in S, and whenever U is a unit in S, F of U inverse will be equal to F of U quantity inverse. One more definition here. If F, going from R to S, is a function, so not just a homomorphism, this is a generic definition for any function here. The image of F is the subset I for image, which is equal to the S elements of big S, the elements little s from big S, such that S is equal to F of R for some R in big R. The book denotes this, S is equal to f of R, such that R is from R. I try to make it a little more elaborate in that set notation concept here. The image of a map is actually all the elements that actually get mapped to. So it's the guys over here in S that get mapped to. Now, if F is surjective, everybody in S gets mapped to. But what if F is not a surjective map? Then maybe not everybody over there in S actually gets mapped to. So the image of F are the elements from S that actually have somebody in R mapping to them. That's what it is basically in English. So the image is basically inside of S, but it's your true range. I think the fancy term for that is the codomain, if you go back and look at your high school algebra books. So the actual guys that actually get mapped to is called the image of F. So what's the big deal? Well, we have corollary 3.11. Corollary 3.11 states this. If phi, going back to my classic Greek letters now, if phi goes from R to S is a ring homomorphism, a homomorphism of rings. Ring homomorphism, homomorphism of rings, that's two different ways of saying the same thing. Then the image of F is a subring of S. There it is. We're going to prove a subring under mapping. As I mentioned to you before, phi is property preserving here. So I'm going to come over here and remind us what the image of F is. So start with your givens. Let's start with given. Given phi from R to S is a ring homomorphism. That means lots of things. Therefore, R and S are rings. Also, we use the same symbol before. Let I be equal to the set of S, elements of S, such that S is equal to, we use the phi now, phi of R for some R and R. Okay? That is I'm going to denote I to be this image. We're going to prove this image, this set, as elements of big S, such that little s is equal to phi of R for some R in R. We're going to prove that set is a subring. How do you prove a subring? Quote your favorite theorem, Theorem 3.6. You got to show me three things. What are the three things you have to show me? You have to show me it's one, closed, it's got to be non-empty. Number two, it's closed under subtraction. And then number three, it's closed under multiplication. Okay? So there's three things you actually have to show me to prove that you actually have a subring. Theorem 3.6. So the first thing I want to show is non-empty. Well, as R and S are rings, they have a particular element. Then 0R is an element of R, and 0S is an element of S. Because they're rings, they have the 0 element. By that famous theorem that we just quoted, you'll quote him a lot in this particular book now, Theorem 3.10. Where do these maps? According to Theorem 3.10, 0 is mapped to 0. So phi of 0R is equal to 0S. Hence, 0S is an element of I, and I is non-empty. All right. Look at that set structure here. To be an I, you had to come from S. 0S comes from S. That element, S, has to be equal to phi of somebody. 0S is equal to phi of 0R. That part's been satisfied. For what's inside that parentheses, 0R had to come from R. 0R came from R. So in my condition to be inside of I, all three things in terms of 0 have been satisfied. So therefore, 0S is an element of I, and I is not empty. Remember, we're trying to show I is an ideal, a subring. I is a subring of S. Okay, so that's the idea. So continuing on. The next thing I got to do is I got to show closure under subtraction. So I need to give myself two elements. What are my favorite elements? X and Y. So let X and Y be element of the set that you're trying to show is a subring, is an element of I. But then you got to tell me what that means. Therefore, X and Y are elements of S, that's where they came from, and there exists, great time for subset notation here, is that, look, S is equal to phi of R for some R and R. So anytime I got R, that's when I'm going to use subscripts. So there's going to exist an R1 and R2. See, R is kind of an afterthought type thing here. That's a great time for subscripts. So there exists an R1 and R2 element of R such that X is going to be equal to phi of R1 and Y is equal to phi of R2. This is the hard part about proving a subring. It's part number 2. Because once you get part number 2 down, part number 3 is going to follow from it. So you've got to, part number 2, give yourself two elements inside the set that you're trying to show as a subring. So let X and Y be an element of I. And then you've got to tell me what property in I do they have. Therefore, X and Y must have come from S, and there exists an R1 and an R2 from R, such that X is equal to phi of R1 and Y is equal to phi of R2. And be careful, this is where most people get messed up at. They'll put the phi on the wrong side. So you're mapping the elements in R. Phi of R1 equals X. X is inside the S, or the range world here. Okay? And Y is equal to phi of R2. We want to talk about closure under subtraction. So, as X and Y are elements of S, then X minus Y is an element of S, because S is a ring. And rings have closure. So you just have to tell me S is a ring, because rings have closure. Let's keep going. Also, X minus Y, this is equal to phi of R1 minus phi of R2 by substitution. Thus, X, as phi of R1 minus phi of R2. Who's that guy going to be equal to? Phi of R1 minus phi of R2. Remember, phi is a homomorphism. So that's going to be equal to phi of R1 minus R2. Don't tell me by factoring. You didn't factor anything. This was actually a property that we discussed by Theorem 3.10. Hence, X minus Y is equal to phi of R1 minus R2, again by substitution. I replace that phi of R1 minus phi of R2 with phi of R1 minus R2. Okay. One last thing. Since R1 and R2 are elements of R, then R1 minus R2 is an element of R, because R is a ring. Therefore, X minus Y is an element of I. Now I'm going to go back and underline again, because you've got to really understand the set notation to make sure everything has been documented of why X minus Y is an I. I started out with x and y and I, and I stated what their properties are. But to be inside of I, you have to come from S. So somewhere I had to state x minus y was an S. There it is right there. X minus y is an S. That's your first part. Where did I come from? What property do I have? X minus y has to be equal to phi of somebody. X minus y is equal to phi of R1 minus R2. X minus y equals phi of somebody. Where that somebody, R, had to come from R. So I had to state that the R1 minus R2 came from R. I stated that right there. So all three properties of being inside of I have been satisfied by x minus y. That puts x minus y as an element of I. And now I'm going to do the third part. The third part of Theorem 3.6 to show you have a subring is I have to show closure under multiplication. So start with your same guys. Just recopy it as x and y are elements of I, same guys. Therefore, x and y are elements of S, and there exists an R1 and an R2 elements of R such that x is equal to phi of R1 and y equals phi of R2. I mean, I literally just copy that first line from showing the closure under subtraction. I'm going to recall it, so instead of let, I'm going to continue on as and copy it exactly. X and y are elements of I, therefore x and y are elements of S, and there exists an R1 and R2 elements of R, such that x equals phi of R1 and y equals phi of R2. I mean, it's completely copied. And I'm going to continue on copying, except remember, where there's a subtraction, I'm going to now put in a multiplication. As x and y are elements of S, then x times y is an element of S, changing the subtraction to multiplication, because S is a ring, and rings have closure. Also, x, instead of minus, it's times y is equal to phi of R1 times phi of R2 by substitution. But as phi of R1 times phi of R2. Now I have to focus on my multiplication properties. Who is phi of R1 times phi of R2 equal to? Well, that's equal to phi of R1 times R2 by definition of homomorphism. Phi was given to be a homomorphism. So by definition of homomorphism, phi of R1 times phi of R2 equals phi of R1 times R2. Thus, x times y is equal to phi of R1 times R2, again by substitution. And as R1 and R2 are elements of R, then R1 times R2 is an element of R because R is a ring. We're really beating to death these definitions and properties. Hence, x times y is an element of I. And again, I'm going to go back and highlight why is x times y an element of I. Again, to be inside of I, you have to come from S. You have to be equal to phi of some dude, where that some dude came from R. So x times y, so is it got to be inside of S, so I stated that here. X times y equals phi of some dude. X times y is equal to phi of R1 times R2, where R1 times R2 had to come from R. So all three things have been satisfied. That's what puts x minus y inside of I. X times y inside of I. So, last statement. Finish it off. I've got one little line. I think I can put it right in here. Therefore, by your favorite theorem, 3.6. I is a subring. And don't just tell me he's a subring. You've got to be a subring of somebody. I is actually a subring of who? S. Why S? Because S is where the elements of I came from. So you're a subring of S. And you're done. Now, as you go back and look at this thing, let's see if I can pull this guy down a little bit so you guys can do this. Okay? As you go back and look at this particular proof, and this is a great proof to study, so you really need to get all the aspects of this particular proof. And again, I tried to write this up accordingly because you're going to be doing a lot of these proving that subrings of under homomorphisms will be subrings. Because as I mentioned before, homomorphisms are property preserving. So if you got phi going from ring R to ring S, subrings of ring R will map to subrings of ring S, so it's property preserving. And later on we'll talk about some of the other aspects of rings and some of the other things that are inside of rings that we can look at, mainly ideal theory when I get into chapter 6. But the idea is that when you get this homomorphic mapping, and isomorphic mappings, these mappings are property preserving. So whatever special property you're going to have in ring R, you're going to have that same special property under ring S. And then the last one is another definition. Get you guys set up for some more stuff here. And the definition is this. Let phi go from ring R to ring S be a ring homomorphism. So phi is going from R to S, be a ring homomorphism. Again, that screams volumes at me that R and S are also rings. But then the subset K, I'm going to call this guy K, which is equal to the elements little r from ring R, such that phi of R is equal to 0 in S. That subset is called the kernel of phi, the kernel of your mapping. Now, who is this K guy? Well, you got a homomorphism. You got a mapping going from ring R to ring S. To be inside a K, you have to come from R, and you got to map to the 0 element over here in S. So in English, the kernel of phi is the set of all elements in R that map to 0 S, an element of S. Now the idea is this. This guy's real special, this kernel of a homomorphism. Again, idea is this. From high school, when we looked at old f of x, and f of x was a function mapping from the reals to the reals, and we were graphing it using our calculators and all that good stuff, we looked at something very special. And that very special concept was the idea of f of x is equal to 0, setting the function equal to 0. And then we focused on the x values. The x values were called x-intercepts, same thing as roots or zeros, depending on which textbook you use. X-intercepts, roots, and zeros are the same thing. The kernel of a homomorphism are these x-intercepts, roots, and zeros. Typically, we're not graphing it, so we're not crossing the x-axis or anything like that, but they are called the zeros of the map. It's the elements in R that map to 0 over here in S. This kernel is going to be playing a very important part in future sections in terms of analyzing homomorphisms, as it played a very special part when we were in high school and setting functions equal to 0 and stuff. So this is section 3.3, and from here we're going to be proving a bunch of more stuff and then moving on to chapter 4.